Hello, everyone. My name is Lining Yan, and I'm glad to be here and give our presentation for the conference CSCI 2025. And I'm the undergraduate student from the Department of Computer Science at Wenzhou King University. Today, I'm pleased to present our work titled Multi-Level Text Feature Analysis for Detecting AI-Generated Content. And this research is jointly conducted with my colleagues Haolu Ye, Tai Lin Pan, and Bahai Naini, and he's also the corresponding author. So in this talk, I will introduce a multi-level feature analysis framework, which designed to distinguish AI-generated academic abstracts from human-written ones, and then demonstrate how combining global and local linguistic signals significantly improves detection performance. So in recent years, large language models such as GPT-4 and Llama have become capable of generating scientific abstracts that often appear indistinguishable from human writers. This raises concerns in academic publishing where maintaining authenticity is crucial. So our study introduces a multi-level detection framework that analyzes both global features at the abstract level, such as coherence, perplexity, and lexical diversity, and local features at the sentence level, such as sentence structure, POS tag patterns, and the token level log probabilities. Across the cheat dataset, we observe clear stylistic differences. For example, human-written abstracts show much clearer variance in sentence length uh, and high lexical diversity. And in contrast, AI-generated text tend to be more uniform, typically between 15 and 30 words, with the TTR around 0.4. So using these insights, our Modern Bird plus Random Forest ensemble achieves extremely strong performance, F1 score of 99% at the abstract level and 93.5% at the sentence level. So the core challenge of AI-generated text is that large language model generated text is no longer simplistic or easily detectable. Instead, it exhibits fluent academic tone, a coherent logical flow, and structural consistency. So the traditional detectors that rely on shallow features such as n-gram frequencies or stylistic heuristic struggle, particularly under adversarial conditions like paraphrasing or polishing. To address these limitations, we combine global and local features in a multi-level analysis pipeline, enhancing robustness when content is mixed, partially rewritten, or adversely modified. We also employ an ensemble model where Modern Bird provides contextual embedding, and Random Forest contributes strong performance on engineered features. Sharp interpretability further reveals that perplexity and token level log probability are the dominant discriminators between human and AI text. So now we explore the related work. Previous research fall in our four main areas. First, feature-based detections shows that AI texts typically present higher linguistic complexity, but lower structural variability. However, polishing and paraphrasing reduce these differences. Second, model level based detection such as XQXGPT, token ensemble, and the detect GPT provides improvements, but each has limitations, especially with short, noisy, or paraphrased text. Third, evasion tactics like recursive paraphrasing or style transfer significantly degrade detector accuracy. highlighting the need for multi-granularity analysis. And the fourth, interpretability research using SHARP has shown that perplexity have and the token probability has strong signals, but most detection systems still lack transparency. And our work integrates all these insights into a unified multi-level framework designed for robustness and interoperability. So here is our methodology framework. So this slide illustrates our full pipeline. We begin with the cheat datasets, then pre-process and clean the text. Next, we extract both global abstract level features and the local sentence level features. These are combined with contextual embeddings from modern BERT. We train our base models and an ensemble model. Finally, the sharp interpretability provides feature importance and model transparency. So this multi-level structure allows us to capture both macro-level stylistics patterns and micro-level linguistic signals that differ between human and AI-generated abstracts. For experiments, we use the cheat dataset. It's a large-scale collection specifically designed for detecting AI-generated scientific abstracts. It includes 4 subsets. The initial subset contains 30,000 samples, 15,000 human abstracts from IEEE Explore, and 15,000 AI-generated ones based on title and keywords. So the second is the polished subset. It contains 15,000 human abstracts polished by ChatGPT. And the third is fusion subset. It's the hybrid abstracts mixing human and AI sentences. And the fourth is the sentence level dataset. It contains 120,000 sentences extracted from all subsets. So the pre-processing include duplicate removal, text length, filtering, illegal character normalization, and porter stemming, store word removal, word frequency analysis, and the calculation of sentence metrics such as complexity. This builds a clean, balanced dataset for both abstract and sentence level classification. We extract 5 core linguistic features. The first is perplexity, measured using GPT-2. Human texts show higher and more variable perplexity. And the second is burstness. It's capturing variance, and in word frequency, humans exhibit greater variation. And the third is the sentiment score. We use VADAR, AI-generated text cluster around neutral or mildly positive sentiments. And the fourth is a token level log probability. Lower values appear in human text and AI text cluster higher. And the 5 is the post tagging. The AI tends to it's applied using the SPY-CY to identify scientific patterns, revealing the formulaic structures in AI texts versus the richer synthetic variety in human writing. And the next is model development and training. We evaluate 5 models. The first is modern BERT. It's fine-tuned with ROPE, embeddings, and local global attentions. The second is BERT, trained with the same hyperparameters. And the third is the random forest. We have 100 trees with max steps 20. And the fourth one is LSTM. We configure with 128 hidden lake units and to add an optimizer to capture sequential dependencies. And the last one is the modern BERT plus random forest ensembles. So the training was used 80% for training, 10 for validation, 10 for testing, 10% for testing. And here is our experimental results. Mm, we'll begin with the sentence complexity and sentence length. In this analysis, we examine dimensions simultaneously: sentence length measured in numbers of words and sentence complexity approximated by the average number of words per clause. So we observe human written text displays wider dispersion across both axes and the sentence length varying from very short 10 words statements to complex 50 words structures. Many human sentences exhibit multi-clause composition and vary rhetorical forms. In contrast, AI-generated sentence cluster tightly in a constrained region, mostly between 15 and 30 words. This uniformity arises because large language models tend to generate sentences that optimize fluency and readability. These differences become even more pronounced in the fusion datasets, where human AI hybrid abstracts reveal a mixture of dispersed human-style sentences and have compressed AI-style sentences. So the next one, we move to the lexical diversity. We evaluate type token ratio, which stands for TTR, and the measure of textual lexical diversity, we short MTLD, which captures short range and long range diversity respectively. For TTR, human written abstract tend to have a value between 0.5 and 0.7, reflecting broader vocabulary use and less repetitive phrasing. And AI-generated text, however, show a narrower TTR distribution centered around 0.4, indicating more repetitive token usage and optimized sentence construction. And for the MTLD, the human written text typically between 16 to 0.7 to the 0.9. But for the AI generated text, it's mostly close to the 0.65. And the next result is related to the sentiments. Although scientific abstracts are expected to be neutral overall, human written abstracts tend to show a noticeably broader range of sentiment scores. So the AI-generated abstracts, on the other hand, tend to converge around neutral or slightly or mostly positive sentiments. So this subtle discrepancy becomes particularly meaningful in the polished subsets where human written text polished by ChatGPT acquires more positivity and losses negative expressions. This is evidence that even partial AI involvement can alter emotional signatures, enforcing the value of multi-feature detection. And next, let's examine perplexity and burstedness in details. So these are two of the most informative stylistic signals. So the perplexity, for the human written text, tend to exhibit higher perplexity, often this linguistic often over 2,000. And this linguistic variation caused greater uncertainty for large language model trained on general corpora. But for AI-generated text, in contrast, show significantly lower perplexity, typically forming a tight cluster. It should reflect al- algorithmic optimization and internal next token probability smoothing. And for the burstness, which capture variation in word frequency, reveals another strong distinction. Human abstract include varied word reuse patterns across sentences, where AI-generated text display more uniform word distribution. Together, perplexity and burstness form a highly complementary pair. Perplexity captures global unpredictability, while burstness capture micro level variability in token usage. The next is the log probability. We could observe for the human sentences, it varied from -14 to -8. In contrast, AI-generated sentence cluster at higher log probability value, often around minus -9, indicating constancy and predictability. So next is the model performance. This table summarizes the F1 score across all model variations. So our modern BERT plus random forest ensemble model achieved the highest, strongest performance across several datasets, include a near perfect 99% on the initial abstract level subset. On the fusion subset, which is more challenging because of mixed human AI content, the ensemble still achieve a relatively strong 78.4%, outperforming all single models. And at the sentence level, the ensemble again reached 93.5%, showing robustness across each model. And so the next is for the SHARP. Reanalysis SHARP provides both global and locally interpretability for our detection framework. At the global level, we quantify the overall contribution of each feature, of the perplexity and the token level log probability emerges as the two most influential feature across all data sets. And secondary contributors such as burstness, sentences complexity, and MTLD, lexical diversity, and sentiment analysis capture additional stylistic nuances that refine classification decisions. In contrast, surface level features like text length and sentence length contribute very little. So here I will going to give our presentation a short conclusion. So the human written abstracts show higher stylistic variability across sentences, length, complexity, and lexical diversity. But for AI-generated content, it's more uniform, optimized, and predictable across multiple linguistic dimensions. And our multi-level framework integrating global and local features successfully capture these distinguishes. And these findings collectively demonstrate the effectiveness of feature level and the context level integration for robust AI text detection. Also, we have some limitation and for the future perspective. So the first, the G dataset focuses exclusively on English scientific abstracts. Detection performance may vary significantly in other language models or in informal domains, such as social media or conversational text. And the second, the ensemble is computationally extensive. And the third is adverse, so robustness remain open challenges as newer large language model appears capable of mimicking human stylistic variability, detection difficulty will increase. So the future research should explore semantic level and discourse level features across linguistic transfer and adversarial training. So thanks for your listening and very much for your thanks for your attention.